I needed to add it to my notes so that I make sure I mention it next semester. And this is on a couple of problems in section 10.1 where we're looking at two means. So section 10.1 was all about conducting a t-test on two means where the samples were independent. So you go through here. So if this is two means, then what would you do? Would you do a t-test for the difference between two independent population means? Is that right? Mm-hmm. Looks right. Okay. And then so they say something about, do political science classes require less writing than history? So I assume the alternative hypothesis would be that H sub or mu sub 1 is less than mu sub 2. So mu sub 1 is less than mu sub 2. Is that right? Do a quick check. Yes, it is. So the null hypothesis would be that it's greater than or equal to, but since I don't have that as my choice, I just pick equal because the null hypothesis must always contain equals. So is that right? Looks good. And now I'm going to go to my calculator and I'm going to put this in my calculator and I'll get the t statistic, right? Whatever that equals. I'll get a p-value. I'll compare the p-value to the alpha and I'll make a decision whether or not to reject or not reject the null hypothesis. And that really is my only two choices, right? I either reject the null hypothesis or I fail to reject it. I never accept the null hypothesis. So I'm going along here and look at what they asked me at the last question. Calculate the 99% confidence interval for the difference in mean numbers of writing pages required for political science versus history courses. How do you do that? I didn't tell you. But if you're savvy, go over to your calculator. Even if you aren't, go to your calculator. So if I go to my stats and my test, do any of those look like they might be something you're looking for? Okay, so you want an interval, right? Interval. So we've got the z interval and the t interval, and those apply to a single sample. So if I go down, look at there. I have a 2 sample z interval and a 2 sample t interval. So what are you interested in doing? A 2 sample t interval. And you can see what A is, a 1 proportion z interval. So we're going to do 0. Okay, and we're going to use stats. And then we just put all that stuff in. So what did we have here? See if I can get it where I can see both of them at the same time. 18.1. With a standard deviation of, oh, that's not my average. Of 42 class was 5.5. Okay. 5.5. Sample size was 42. And the second average is a 20.4 with a standard deviation of 4.8. And the sample size was 53. Let's go up so we can see what we're doing here. Okay, then you need to put the confidence level in. What was the confidence level? 0.01, what are they telling, what are we doing? 0.99%, okay. 0.99. No, I'm not going to pool the variances. And then calculate. And that should give me the Looks weird. I think I got everything in there correctly. Looks kind of odd. Let's go back and see what the answer is. Yep, I got it right though. And since the confidence interval is looking at the difference in the two means, so it's a confidence interval where you're confident, 99% confident that the true population difference in the means is between those two values. I said it looked odd because it was negative, but that's perfectly okay, because you could get a difference of the two means being negative. But that's where it's found, is in your tests. Where was that again? In your tests, 2 sample t interval, because you're doing a t statistic, a t-test, but you're looking at 2 different means. So anytime it asks you for a confidence interval, when you're looking at 2 independent samples, that's what you're going to use. Okay. All right. We're going to today look at matched or paired samples. So on Tuesday, we looked at what we just talked about, 2 independent samples. So one sample in no way, shape, or form depends on the other. Now with matched pairs, that's not the case. Okay? So when you're using a hypothesis test for matched or paired samples, the following characteristics should be present. Simple random sampling. The sample sizes are often small because you're not looking at a huge group of people or plants or whatever. 2 measurement samples are drawn from the same pair of individuals or objects. Differences are calculated from the matched or paired samples. And that's what you're going to run your hypothesis test on, is on the difference in the before after kind of whatever your data is. You're going to get 2 sets of data from each object or person, and you're going to compare those 2 by taking the difference in the 2. Either the matched pairs have differences that come from a population that is normal, or the number of differences is sufficiently large so that the distribution of the sample mean of differences is approximately normal. Okay. Now, the statistics for this and all the other stuff are rather complicated to calculate. That's why we're glad we have a calculator. In a hypothesis test for matched or paired samples, subjects are matched in pairs and differences are calculated. And your calculator can even calculate the differences. That's how I'm going to show you to do it. The differences in these 2 means are your data. So that's the data you're interested in, is the mean, is the difference of the 2 means. The population mean for the differences U sub D is then tested using a student's t for a single population mean with n minus 1 degrees of freedom, where n is the number of differences. So the test statistic, the t-score, is found by the mean of the differences minus the population mean of the differences divided by the standard deviation of the differences divided by the square root of n, the sample size. Okay, so we're just going to dive right into an example. Does everybody have a calculator today? If you don't, I have 2 up here. You can borrow one. So we're going to actually run through this entire thing. So I would like for you to put this in your calculator, please. A study was conducted to investigate the effects of hypnotism in reducing pain. Results for randomly selected subjects are shown in table 1011. A lower score indicates less pain. The before value is matched to an after value, and the differences are calculated. The differences have a normal distribution. Are the sensory measurements on average lower after hypnotism? Test at a 5% significance level. So what I did, I put the before in L1 and the after in L2. So go ahead and do that if you haven't already. Go ahead and put that data. And I do have it in a column if that's a little bit better. I'm sorry, I put the after in L2. It doesn't really matter. No, I put the after in L1. It doesn't matter. I'll show you why it doesn't matter where you put it. It doesn't matter where you put it. It just how you take the difference is going to change. Have you got it in? Okay. So like I said, it really doesn't matter where you put the before or after, but what we're interested in is the difference. So you could calculate these differences, which is what they did, and then put that in a list. It's too much work because your calculator can calculate the difference for you. Okay, so since I put my after data in L1 and my before data in L2, and I'm interested in the after minus before, what that score is, I'm going to subtract L1 from L2, L2 from L1. Now, it depends on what yours is, if you're how you're going to subtract this, but let's go do it. So I have my after data in my L1 list and my before data in my L2. So I'm going to go over to L3. And I'm going to go up, and I am actually going to type in that I'm going to subtract L2 from L1. So I'm going to type in that L3 label L1 minus L2. So I go second L1 minus, you can see down here at the bottom, L3 is going to equal to L1 minus L2. And when I hit enter, it will calculate the differences for me. Is that what you guys got? Did you get 0.2, negative 4.1, negative 1.6, negative 0.8, negative 3.2, negative 2, negative 2.9, negative 9? Wow, negative 9.6. Woo! Hypnotism helped that person. So what this means is, it looks like from just the differences that only one person hypnotism didn't help at all, that their pain actually went up. Their pain level went up. Okay, so let's go back to our PowerPoint and let's write a few things down. Okay, so first of all, a study was conducted to investigate the effectiveness of hypnotism in reducing pain. Results for randomly selected subjects are shown. A lower score indicates less pain. The before is matched to an after value, and the differences are calculated. The differences have a normal distribution. are the sensory measurements on average lower after hypnotism? So what we're interested in is the difference lower. So is the after less than the before? Or is the difference less than 0? So that's what we're interested in showing. Is the difference after hypnotism lower? Is the pain level after lower than the level before? So let's write that down. So is the level after lower than it was before? Or is the difference less than 0? Or we're going to write that as U sub D. Is that less than 0? And that's going to be our alternate hypothesis, alternative. So our null hypothesis will be that it isn't less than. And our alternate hypothesis is going to be that it is. Okay? So now to do this test, we are going to do a student's T on the mean differences. So we're going to do a student's T on that third column. So we're going to do a student's T, and we had how many sample points? 1, 2, 3, 4, 5, 6, 7, 8. So the degrees of freedom is 8 minus 1, which is 7. So we're going to conduct a t-test. Woohoo! We're going to conduct a t-test, and my data was in L3. Okay, so I'm going to get out of here. I'm going to go to my stats tests, and my t-test is number 2. Okay, and I'm going to use my data. And we're looking for, is the mean different than 0? Is that mean difference different than 0? So my mu sub 0 is 0. I'm going to use the list that I put my differences in, which was L3. I am interested in a less than test. So I'm looking at a left-tailed test because my alternative hypothesis was, is the difference less than 0? And I'm going to calculate. Okay, so my t statistic is negative 3.035907687. My p-value is 0.00947798878. The mean of the differences is negative 3.125. So on average, after hypnotism, the pain was reduced because that is a negative value, and the standard deviation is 2.9. Okay, so let's go back to our, and let's make a decision here. So we got our t statistic was negative 3.0359, and our p-value was what, 0.0095. And what are we testing at? Alpha equals 5%. That's PowerPoint breaks. Okay, so what decision are you going to make? If the p is low, the null must go. So since p is less than alpha, you're going to what? Reject the null hypothesis. So what does this data show? The data supports the conclusion that the pain level goes down after hypnosis. because our alternative hypothesis said that after was less than before, or the difference is less than 0. So the pain level is negative because it goes down. So our data, our sample data, does support the conclusion that hypnotism works in reducing pain. Is that what you guys got for your p-value and your? So since we compared alpha and the p-value, alpha is 0.05, our p-value was 0.0095. Since p is less than alpha, we reject the null hypothesis. This means that the mean difference, the mean of the differences is less than 0, and there is an improvement. So at a 5% level of significance from the sample data, there is sufficient evidence to conclude that the sensory measurements on average are lower after hypnotism. Hypnotism appears to be effective in reducing pain. Okay, let's try another one. A college football coach was interested in whether the college's strength development class increased his players' maximum lift in pounds on the bench press exercise. He asked 4 of his players to participate in a study. The amount of weight they could each lift was recorded before they took the strength development class. After completing the class, the amount of weight they could lift, each lift, was again measured. The data are as follows. So the amount of weight lifted prior to the class for each of the 4 players, and the amount of weight lifted after. Now, you would expect, if his conclusions are true, that after would be more than before. So what I would do, and it really doesn't matter, I would probably put after in L1 and before in L2, and then whatever I have written in L3, L1 minus L2 will still work. Now, if I put it the other way, I just change the difference. So why don't you go ahead and do that? It's only 4 data points. Are you done already? No, I haven't done this. I'm gonna have to go do it. You only have 6 lists. So, something's got to give. Let's see if I can do this where I can see both of them at the same time. Okay, so I am going to clear out my 2 lists. Okay, so what did I say to do here? I put after in L1. Okay, and I'm going to put before in L2. like watching paint dry, watching me put data into the calculator. Okay. And let's go over there and clear that out. And we're going to let that be L1 minus L2. Okay, let's blow this back up. And holy moly, we got a 90 there. I don't know what's going on there. I don't know. This data looks weird. This person lifted 90 pounds more after either the class really worked or something was going on during the first sample. Anyway, okay. Get out of here. And let's go back and let's talk about what hypothesis we want to write. Okay, what are we trying to show? We're trying to show that this class made a difference, right? The coach is interested in whether the college strength development class increased his players' maximum lift in pounds. So he's thinking that after is better than before. So after minus before is greater than 0. So that would be his alternative hypothesis. That the difference is greater than 0. So the null hypothesis would be that it isn't. And you could write this, again, remember, you can write this as less than or equal to or just equal to. It doesn't matter. Okay? So now that we have this all set up, let's go run our test. And we're just going to run a t-test on that data if that's in L3. Okay, so I'm going to go to stat tests. I'm going to run a t-test on the data that's in L3. This will all work, except I want, what's my alternative hypothesis? Is it greater than? So I need to change this to a right-tailed test. Okay, so I got T is 0.91 and P is 0.21, and the average of the differences is 21.25. That 90 just took over that average, didn't it? So that's one thing that we recognize about the mean from early in the semester. Since the mean uses every value in its calculation, it can be greatly affected by outliers. Because look at the standard deviation. The standard deviation is 46.7. That's huge. Okay, so our p-value is 0.21, t was 0.91. So t p. So our alpha was 5%. Okay, so if the p is high, then almost fly. So you do not reject the null hypothesis. So what's that mean? Well, this sample doesn't warrant rejecting the null hypothesis that the mean difference is less than 0. So it doesn't look like after is greater than before. And the reason, even though got that 90 in there, the reason that happened is because the standard deviation is huge. So it makes quite a bit of difference in the calculation of your p-value because that standard deviation is so big. So if the level of significance is 5%, the decision is not to reject the null hypothesis because alpha is less than the p-value. So what's your conclusion? At a 5% level of significance from the sample data, there's not sufficient evidence to conclude that the strength development class helped to make the player stronger on average, even though that one person lifted 90 more pounds, the standard deviation was so huge, it affected the p-value quite a bit. Okay? So as you can see in this section, all you're going to do is calculate the differences between before and after or whatever, and you're going to run a t-test on that data. And then you're going to find the p-value, compare it to alpha, and reject or do not reject your null hypothesis. Okay, so this is the last one. Things get a lot less strenuous at the end of the semester, and we're not covering near as much material as quickly as we did at the beginning of the semester. Try to make it easier. It's the spring. What are you going to do? 7th, 8th graders at Kennedy Middle School measured how far they could push the shot put with their dominant writing hand and their weaker non-writing hand. They thought that they could push equal distances with either hand. The data were collected and recorded in this table. Conduct a hypothesis test to determine the mean difference in distances between the children's dominant versus weaker hands. Test if it's significant. So can they push it significantly farther using their dominant hand as compared to their weaker hand? So you can either calculate the differences and then put that in a list, or as we've done before, put the dominant hand data in one list and the weaker hand data in another list, and then calculate dominant minus weaker. So whatever you want to do. Now, this example, they did calculate the differences. There was not that many, and it was a pretty easy calculation to do. The first student is 2, the second student is 8, the third student is what? Is that 7? That's not 8, that's 12. I can subtract. That's 7 minus 1, 2, 0, and 4. So there are the differences there. That's what I'm going to put in my calculator. And I'm going to put that in L4. Did you want to put this, whatever you want to do? So I'll leave that data up there for a second. Let's just go ahead and put those differences on the slide. So you can choose which one you want to do. So 2, 12, 7, -1, 2, 0, and 4. Are we done? Okay, so I'm going to just put that in L4. Why not? So we had 2, 12, 7, -1, 2, 0, and 4. Make sure I have that in correctly. Okay, so let's go back and let's look at some hypotheses. So what are we trying to show here? They thought they could push equal distances with both hands. So what these students think is that the dominant hand is the same as the weaker hand. There doesn't make any difference whatsoever which hand they push this with. So the difference in the dominant and the weaker would be 0. And I use D for dominant, but we also use that for difference. Maybe I should use M for dominant or something. I don't know. So they're trying to show that there is no difference in either hand. So that is their null hypothesis. So their alternate would be what? That there is a difference. Okay, so now you're going to conduct your t-test on those differences using a two-tailed test. Okay, so let's go over there. Let's do that. Make it bigger. All right, so we're going to go to stat, tests, t-test. From my data, I'm going to use, what did I put that in? L4. And it's a two-tailed test, so I'm going to use not equal to. Calculate. So I get my t-statistic to be 2.184 and my p-value to be 0.07. Okay. So my t-statistic we calculated t to be 2.184 and p to be, what did we calculate p to be? 0.07. Now this is a two-tailed test, so half your p-value is in each tail, but your calculator calculated it to be 0.07 because you told it it was a two-tailed test, so it calculated it properly. Okay, so now what are we going to do? Our alpha was what, 0.05? Is that what we used for alpha? Yes, it is. Well, our p is greater than alpha. So if our p-value is higher than alpha, then we do what? We fail to reject. So what's that mean? Well, what were they concluding? They were concluding that there wasn't any difference. And the data, there's not a significant enough data to warrant rejecting that claim. So the data doesn't support the conclusion that there is a difference in their dominant and weaker hands. So assume alpha is 0.05 at a 5% level of significance from the sample data. There's not sufficient evidence to conclude that there is a difference in the children's weaker and dominant hands to push the shot put. What's that mean? One arm's not stronger than the other just because you use one hand more dominantly than the other, is basically what they're concluding. All right, are there any questions? Now I did push out your due dates. Let's go take a quick look. And I uploaded the new schedule to Blackboard. So we finished 10.4, and that is due Monday. And 10.3 is due next Wednesday. And we can easily do 10.3 on Tuesday. It's not all that complicated. It's on comparing to proportions. And we're not going to do it using the formulas. We're going to let our calculator calculate the p-values for us, etc. So are there any questions? I'm going to let you go early then, if there aren't any questions. And we will see you on Tuesday.